A very warm welcome to each and every one of you at TechWari 2.0. My name is Simran, and it is my privilege to be your host for a technical session on quantum computing, its use cases, threats, and development. On behalf of the General Administration Department, I extend a heartfelt welcome to our distinguished guest and to all the officers who have made time to be here today. Everything we encrypt today, every citizen record, every government database, and every secure transaction is built on assumptions that a quantum computer will eventually break. This is not a distant threat. The race has already begun, and the question for every officer in this room is, are we in it? Our speaker today has been helping governments and industries around the world to understand and prepare for the quantum era. Dr. Amith Singhee is Director of IBM Research India and AI CTO for IBM India and South Asia. He, he leads a research agenda spanning AI, quantum computing, cybersecurity, and cloud. What makes today special is that Dr. Singhee has already engaged us with On Quantum Day, where he spoke about quantum safe cryptography and what government needs to do now. In many ways, he has already been speaking with this room. I now request Dr. Rajesh Kaminde sir, Secretary FTI and Chief of Protocol to come forward and felicitate our distinguished speaker. I now request Dr. Amit Singhee to please come forward and address us.
I have this. Is this working? Okay, very good. And good afternoon, everyone. I know this is before the lunchtime. Hopefully, it's interesting enough to keep you interested in it. Thank you for your attention today and this opportunity. I attended the prior talk, and it's very inspiring to see all the steps the government is taking. When the Singhi talked about to really become technology first, to drive better governance and citizen empowerment. Today I'm going to talk about quantum computing, some of the opportunities that it is presenting to us in the coming years, some of the threats it's also going to present to us, and some initial thoughts on how we might prepare for that. Uh, so let's take a view through that. It'll be a bit of a high level talk rather than going too deep into any for the domain. I think you have to share this slide. Yes. Hindi I will try. Yes. So, so in when we say quantum computing is very different from our normal digital computers, right? And at the core of it, there are three principles that create the power of quantum computing. And here we are showing these three, what happens. And these are coming from quantum mechanics, right? Quantum mechanics means when we get to a domain which is smaller than an atom, like electrons or light photons, they don't behave like normal objects like this, right, that we are used to.
Like a normal object we can know कि अच्छा ये अगर यहाँ है तो यहीं है, और अगर ये इस स्पीड पे मूव हो रहा है तो इसी पे मूव हो रहा है. But if you take an electron, you can't be sure where exactly it is and what speed it is moving at. When you observe it, you will say, okay, it's moving at this speed, but that is when you observe it, it chooses a particular location and speed. But when you're not observing, it stays in a what we call as a wave function. Means it has a chance of being here or here or here or here, but you can define that equation of what is the chances of being in different places, right? उसको wave function बोलते हैं. So because of that nature of quantum particles, they express these three things. One is superposition. That means one quantum particle can exist in multiple states with different probability, which is very different from a bit. एक कंप्यूटर में क्या है, या तो वो 0 हो सकता है या 1 हो सकता है, दोनों एक साथ नहीं हो सकता. बट इसमें क्यूबिट can be 50%, 60% in 0, 40% in 1. You know that it entanglement means that you can take two qubits or say take two photons, light के जो particles होते हैं, entangle them in some way so that now if you take photon number 2 to Mars and then you change something about photon 1, photon 2 will also change, right? Which is strange, it's like magic, but it happens at a quantum level. And interference means that two quantum particles can interfere with each other and impact the state. So quantum computing में all these properties are actually used fundamentally to define कैसे computation होगा, right? Which is very different from normal machines, whether it's GPU, CPU, जो भी आप ले लीजिए, उसमें these things are not there. They are very defined. They are like how we think normally, 0, 1, addition, multiplication, like that. So I want to give you that sense कि okay, it's a very different kind of a thing. Now, where does it become useful? And this is a little bit computer science theory lens, but I'll try to make it simple. In this circle, imagine all the ways we use computers today. All the things that we use it for, whether it's data integration or weather modeling, all kinds of things, right? We call these as classically tractable, means कि उस problem को you can use even a supercomputer or a laptop, whatever, you can use it to solve it in some reasonable time. Reasonable may be a year, right? But it's reasonable. But there are classically intractable problems. For example, अभी जो हम cryptography use करते हैं, encryption use करते हैं, there is something called RSA codes. RSA codes use a secret key, and you can get the key, but you won't know how to break it, right? Because it is very difficult. What you have to do is you have to find the prime factors. You may remember prime factors, like 15 ke prime factors are 5 and 3. But if I give you a number which is hundreds of digits, finding the prime factors of that, even with the biggest supercomputer, you cannot do it in years. That's why we call it classically intractable. ऐसे कई सारे problems हैं. And either we have used those to create cryptography, or we have said we can't solve those problems, so we don't solve them today. Or we simplify them in some simple way to solve it approximately to make it classically tractable. That's what happens today. When we use quantum computing with those properties I said before, the theorists have projected that once quantum computers become powerful enough, we will be able to solve some of those intractable problems, and maybe there's some new problems that we haven't even thought of, right? So this is one way to think about it. These things are the skip, okay? Now, what are these problems that I'm talking about that could be where quantum can really help? There are 4 types of problems, and I will translate these two into specific use cases in coming slides, right? But these 4 types of problems, one is what we call Hamiltonian simulation, means basically simulating the nature of quantum behavior at a subatomic level. Like I told you, electrons don't behave like normal objects. लेकिन अगर आपको, let's say you have to discover new drugs or new vaccine, for COVID or something like that. What happens is there is some protein molecule that is on the germ, on the virus or on the bacteria, and you want to find a chemical that can go and attach to that and stop its action. If you don't have a molecule, so when we take the tablet or something, it basically goes and it will attach to it and it will stop the action of that bacteria. Now, to do that, you have to understand the structure of that protein, like how is it organized, how do the electrons behave, so that if I make a new drug molecule, it should attach. If it doesn't attach and doesn't block it, it's no use. Today, what happens is chemists will do years and years of trial in the lab. It takes years to find something. But if you can simulate how that molecule is actually behaving, and you can simulate also how a potential drug molecule might attach or not, you can speed up this whole cycle, right, in the computer. But for that, you have to actually simulate that quantum mechanics of the superposition and all that of the electrons, which large supercomputers also can't do. That is what I mean. Hamiltonian simulation means basically simulating the quantum mechanical nature, how the nature works at that very low level. Or in batteries, for example, these new batteries of lithium ion and lithium air batteries, they have a lot of potential of storing a lot of energy, but today we haven't reached that potential. If we do, then we can really progress our green energy future. To do that, again, you have to understand that how the lithium ions bonds with other atoms are working, when do they break, how can I use the right chemical processes at that level. You need to simulate nature at the quantum level. Second class of problems is optimization. Means you have many variables, choices, and you have to decide the right choice. For example, for investment banks, what is the right portfolio to manage so I get the most return at the lowest risk? So they have thousands and thousands of choices of this stock, that stock, these bonds, how much to hold, for how long should I hold. And today they do it using some approximate mathematics. But they are doing something like what I said, taking the hard, unsolvable problem, but making a simpler version of it to solve it with today's machines. But if we could solve it in more accuracy, then you can come up with better answers. Third area is machine learning. Of course, machine learning, AI has made a lot of progress already. We all know that. But still there are places where you can push more. If you get a data set within which there is some pattern, but the pattern is hidden, you cannot observe it even if you apply today's AI. Quantum has this promise of transforming the data into some way to reveal the patterns even better. And then you can apply today's AI on top of that transformed data to do a better job, right? Fourth area is differential equations, which is also about simulating nature, but not at the quantum level, at our normal level. For example, turbulence for aircrafts, right? So today when you want to optimize the wings of aircraft and all that, there are simulations people do, and you have wind tunnels and all of that. But if you want to make it more accurate, you need to solve the differential equations of how the airflow will happen. One important area is submarines, and modeling the hydrodynamics of submarines or torpedoes. That's not an easy problem, and there's promise that once quantum computers become powerful enough and people understand how to implement that problem in a quantum way, then we think that it will also help in this kind of differential equation. These are called differential equations. So these are four types of problems. So you can see these are different from, let's say, digital integration or what we use today's computers for business. These are more computational type of core computing deep type of things, but they can have very big impact in where we want to go with technology as a society. This is just mapping it to some industry sectors, right? The same things I said in a different view. Aerospace industry, where you're looking for high strength to weight materials, you're looking at computational fluid dynamics, wing composite design, In the automotive area, batteries, vehicle routing optimization when you have large fleets. In chemicals, finding better fertilizer manufacturing process, efficient catalysts. In electronics and semiconductor domain, energy domain, financial services, healthcare and life sciences. So many different industries, and actually many companies are already looking at, okay, I have this problem. Like if you go to a industrial company, like a chemicals company, they know that they want this, but they don't know how to use what quantum means for that, right? So they are starting to do this R&D to understand quantum and to understand कि इसको मैं use कैसे करूँ इस problem के लिए. That is sort of where things are, at least with the leading companies globally, right, who are willing to invest in the research, early research, because उनको result आज नहीं मिलेगा, result उनको 5 साल बाद मिलेगा, but they will be the first movers, they will have the competitive advantage. I thought I'll give you a sense of who are all the vendors and maybe express my pride about IBM also. In the market, there are many providers for quantum computers today. They have many different ways that they have implemented the machine. Some are using superconducting qubits like IBM, like Google. Some are using neutral atoms, some are using trapped ions, some are using photons. All these are basically different ways to create that qubit. A qubit is a quantum particle which has those three properties I said. You know, it behaves like electrons, but you can control it. An electron you can't control, it's just there doing what it is. But you need to be able to control and program it so that you can create a quantum program. That's when it becomes a quantum computer. And I'm proud to say IBM today is most ahead in the capability of our machines and the adoption of our machines. What's happening globally? The expenditure, the investment in this space from the potential users doing POCs is substantially going up. And you can see year by year the number of POCs across so many different industries is just ramping up every year. And this is only till 24. The future after that is even more. Unfortunately, I don't think any of these are yet in India in this list. And that is what we are hoping very soon will change, and we'll start having some of these POCs happen in India too. And states can play a big role, because states is where you can actually bring people together on the ground. At the center, NQM has done a great job to create a framework to catalyze research and so on, but then the actual economy happens at the state level, and hopefully we'll see more action from India in this space. Let's talk a little bit more about use cases and some examples. So one area is logistics. I thought I'll start with logistics because it's the least complex, but then we'll get to more and more complex ones. So many areas in logistics, last mile delivery and multimodal transport. You can imagine last mile delivery for a large delivery operation is very complex optimization problem. So many vehicles, should I use a truck, a bike for this one, that one? Yeah, you can do it today, but if you want to do it with 5% less expense and 5% better outcome, pushing it more for competitiveness, that's where the value comes. And as the optimization algorithms on quantum computers get better and better, this is an area it can help. Vehicle routing, scheduling, it's related to this, but not just for last mile, but in general. You have a fleet of vehicles doing anything. How should they be routed to deliver things or to achieve tasks? How should I schedule them? Forecasting the demand, right? This is more of maybe a machine learning type of a thing, where I have many places that I distribute. There's a distribution and I want to forecast the demand. Again, this is a place where quantum can help. Global supply chain optimization. When you have large supply chain operations, like Apple has big supply chain operation of their phones and all of this, or oil companies, petroleum companies. So optimizing all the way from procurement, production, storage, and so on, to do end-to-end optimization to push your metrics even higher. And then identifying potential disruptions, how to mitigate. So if you want to simulate what might happen because of, let's say, weather or war or whatever, those scenarios, and plan for, okay, in those, how should I re-optimize? All of these things are places where we believe quantum can help to improve your results compared to classical. One example is what ExxonMobil tried a few years. They did some collaboration with us. In 2021, for instance, they had 500 liquefied natural gas ships, right, in a year to transport LNG across the globe. And they make thousands of journeys in that year to destination ports, right? And that powers critical infrastructure. Now, this is a very complex, large-scale optimization problem with many, many variables of, okay, which docks, which ports in between are there, and demurrage charges, and uncertainties that come because of weather, and changes in supply, demand, production, so many things. And they've been trying to use quantum to see if they can come up with a more optimized answer to this problem. Let's take financial sector, which is a big one in Maharashtra. This is from HSBC, where HSBC, one of the things they do is trading in the bond market, corporate bond market, right? And what happens is, let's say you want to trade and someone says, okay, these bonds, now you have to bid, like you do on eBay or something, right? So you say, I will bid so many rupees for this bond. But you want to know what is the chance that my bid will be fulfilled. Because based on that, you might increase the bid higher or lower, right? All that matters. So this is a kind of a prediction problem. And they use normal machine learning type techniques where they take all the historical data of, bidding and all of that. Then for this new bond, they look at its properties and then they say, try to guess, okay, if I bid this much, what is the chance of fulfilling? If I bid this much, because they want to bid the lowest possible that has a decent chance. If they bid very high, of course, they will get it, but they don't want to. So what? And here what they did is they used a quantum computer to do what I had said earlier, that to all this data, they use a quantum computer to transform it into some other numbers. Then they used a normal machine learning on top of that. And they saw 34% improvement in the accuracy of that bid fulfillment probability. So this was very exciting. It just came out late last year. Another example is Vanguard, which is an investment company in the US. They manage basically investment portfolios. So portfolio optimization is a big deal for them. And here they took, like 109 bonds, and they said, okay, what is the right combination for me to get the, least risk and most reward? Here also they saw that they could get to within 0.5% of what is the best possible. And they're continuing to work to make it better and better so that they can work not just with 100 bonds, but with thousands and thousands of bonds. Okay, changing topic a little bit, another use case around battery. Batteries are relevant to us in India also. So here, this is a battery, I think lithium ion battery aapko sabko pata hoga. But lithium air battery is a new technology which promises, here you can see, ये yellow जो bar है, it says energy density per kg. कि 1 kg gasoline में how much energy density is there. The more energy density you have, of course, with less you can store more. That's what we want. Lithium air has a potential almost close to gasoline, which is very, very promising. But we're not there yet. Now, how to make the lithium air battery chemical design get to that level is one of the scientific problems. So यहाँ पे Mitsubishi Chemical, which is a Japanese-based company. So Japan is actually probably one of the leading countries in using quantum today. They are trying to model ये lithium atoms जो हैं, they make a particular structure with oxygen to understand कि उसका chemistry क्या है, the quantum level, how does it behave, how does the energetics of it behave. If they can understand that better, then they can come up with ideas of pushing this higher, right? Things like that. Another one I think is very relevant to us in India, fertilizer. So nitrogen fertilizer is a big deal. Because for growing crops, you need nitrogen. And when you grow crops in one cycle, two cycle, वो nitrogen deplete होने लगता है. And you put fertilizer to get nitrogen back there. Today there's a lot of overuse of fertilizers and all that is there. But also the process of making fertilizer takes about 2% of the world's energy. And as the food demand increases, this is also going to shoot up. Question is, can we reduce the energy required to make fertilizers? Can we make the fertilizer manufacturing process more efficient? Now that is again a chemistry problem. Or उसमें one of the key things is this catalyst. It's called FEMOCO, उसका एक chemical compound है जिसमें iron atoms होती हैं, sulfur atoms होती हैं. It is like a catalyst which is used to make the fertilizer. What it does is, in the manufacturing process, it creates the situation for the fertilizer to get formed. And question is, can you make a better catalyst that needs less energy to make that fertilizer? So here some work was done by RIKEN, which is a supercomputing center in Japan. Think of it like CDAC, kind of, right? Working with IBM, where they took IBM quantum computer and a big supercomputer and used it together to try and simulate this iron sulfur combination, atom combination cluster, which is a key part of this process. To see, can we simulate that accurately using quantum classical combination? Sorry. And they saw a lot of progress there. There's a long way to go, but this is just an example of the kind of things people are trying to do. Last one. So as you can see, I'm going to more and more technical ones, but this is also very interesting. Here, this is a protein structure, right? Isme every dot is, you can think of it as an atom. Now, our body works with proteins, you know that, right? Everything is proteins, all the processes in the body. Even bacteria use protein, everything is protein. But simulating the protein to find the right drugs I described earlier is a big challenge. And today it's all done with trial and error. Very recently, this was 4-5 months ago, Cleveland Clinic, which is a research center in US, worked with IBM to show how you can take this. This is a small protein actually, just 300 atoms. How you can take a protein like this and calculate all its electronic details and all of that using a combination of a supercomputer and a quantum computer and get a very good accuracy. Now that is fine, that you can also do with just supercomputer. It was the first step. Actually last night just a news came out, I didn't have time to put it, where now they've gone from 300 atom to a protein which is more than 12,000 atoms. And this is a protein that is made in our pancreas. It's involved in a lot of the process that our pancreas does. And they've shown that they can simulate that to a very high accuracy with a combination of quantum and classical. So very rapidly advancing field in terms of trying to model these kinds of things. They haven't created, these are known proteins, they exist, but what is not known is, if I want to make a drug to attach with that protein, I need to understand the details of how the protein works. That is what they're trying to calculate. Yes, yes. Let's say if some mutation has happened, right? Or if you're overproducing that and you want to have some drug that can, right? So these kinds of things. It could be used for even mRNA vaccines. There's a virus pe proteins hoti hain. So you may know that this protein is there, but you don't know that if I put a drug to it, will it make a bond or not make a bond? These kind of simulations will help you with understanding that. Okay, so that's what I had on use cases, a little bit on how India is looking at it. Of course, the National Quantum Mission, I didn't put much on it. This one I put here, I thought it'll be useful. It's a report from Niti Aayog that was released in fourth quarter last year. Niti Aayog has been doing this Frontier Tech Hub initiative, very good initiative, looking at many of the emerging technologies and creating roadmaps as recommendation for India to see how to use those towards Viksit Bharat more ambitiously. So we had the privilege of working with them on the quantum roadmap, where this is not an IBM point of view. This was actually from consultations across the Indian ecosystem, and putting that together. And we came up with a vision of where India could be in 2035 if we want to be amongst the top 3-5 nations in this area, right? And we came up with these 5 dimensions to that vision. We would like to have at least 10 quantum champion startups with cumulative 100 million revenue each, selling globally. We want to have captured 50% of the software and services business, which today we do in non-quantum, so why not in quantum too? We should have quantum technology deployed across at least 3 major sectors in the country, right? Not just outside. Self-reliance in key parts of the supply chain, very important. And then very, very important is to become a hub for scientific breakthroughs in quantum, right? And to make these happen, the report calls out 7 recommendations of what needs to be done within the next 1 to 3 years so that this actually can happen in the next 9 years, right? So it may be a good.
What are the actual critical components in the supply chain for quantum?
There are quite a few. There's a full quantum stack and supply chain that we call out in the report. There's of course materials. There's a number of materials that come in, raw materials that come in. But then there are also technology components, like electronics, QPUs, the quantum processing units, the cryogenic electronics. There's the software components, that let you run the software. So at different level there are things, and it's important. Like we will not own everything, right? That's not that everything will be indigenous. Then we'll keep waiting forever. But we need to start having presence in a number of those in a very strategic way.
I have a question for you.
Yeah.
Do you have any use cases from anywhere in the world, in specific government sectors or in public finance?
Government sectors, I'm just thinking about it.
Whenever we are thinking about government sector, basically GRC framework is around this governance, risk and compliance.
Yeah.
Compliance is, for example, tax compliance. If somebody will become, for example, we are coming out to DTDP. It's a plethora of things that happen. So if you have to measure the compliance, it will not be possible for us to.
Yeah. See, I think nothing off the top of my head right now, because those 4 categories I talked about, right? Hamiltonian and optimized. So it has to fit in that kind of a problem. Some of these things will be handled through our normal classical computers, right? AI and all that. But things like if there's anything that can be mapped into an optimization problem, things like that. Speed up service delivery. Yes, that area we can explore.
If you have I don't know if DOG explored it in the US or
Yeah,
research
yeah.
use has been there, because that's what they were supposed to use, the latest and reform the administrative process.
Yeah.
It was a part of the.
I haven't seen one. Maybe we can be the first here to do something. Okay, so moving into, where is all this today, right? Okay, all these promises there, but where are we in terms of maturity? This is how we see it in IBM. 2023 is when we came up with this machine which had over 100 qubits, and in a collaboration with University of California, Berkeley, they showed that now you can do things with the quantum computer that you can no longer simulate with a quantum simulator, right? So a lot of people use quantum simulators for their R&D, where underneath it you're using GPUs and not using those superposition and all those things, right? But now we are in a regime where what a quantum computer does at 100 qubit scale, you cannot even simulate it on a classical machine, no matter what you do. You can call it a quantum simulator, but it's not actually simulating. So now whatever people are trying, those examples I gave you, are actually trying to find real useful things with quantum rather than just just playing around, which is why we call it quantum utility era. And in 2026, which is this year, we are anticipating this year, someone is going to show in one of those some use case area, something that quantum computers can do better and no classical computer can do it as well. So that will be an important milestone because that will create a confidence that, okay, this, at least in that domain, maybe it's physics, maybe it's chemistry, this is better. 2029 is the one I want to take your attention to, is when we expect to put out what we call a fault tolerant quantum computer. Today's quantum computer, what happens is those qubits and all, you can program them and run a program, but then after about 100 microseconds or so, they lose their quantum mechanical property that I was showing, some entanglement, because of the noise. They're very sensitive to even very gamma ray noise, things like that. But a lot of work is going on in error correction. Means even if something goes wrong, it will fix it. Like in our laptops, there is a RAM. We don't even think that the RAM's memory will go bad, right? In the middle of my Excel work. Why? Because 50 years ago, someone figured out that if some data goes wrong, how to fix it. There's actually a circuit in there to keep checking for the error and fixing it. So same kind of research is happening for qubits. It's called error correction. And by 2029, both the hardware and the error correction will reach a stage, at least for the IBM machines, that we will put out a fault tolerant quantum computer with 200 logical qubits. Okay, so that means you can run a certain size of problem, but you can run it almost for as long as you want. This will take us into a new paradigm of truly quantum algorithms and applications. And then by 2033, we expect to scale this up to 2000 qubits. So around early next decade, you'll start to see a really ramp up of more activity is what I'm trying to say. Which brings us to the next part of the talk. Let me just see how much time I have. Okay, I have about 20-25 minutes. Which is the threat. We talked about opportunities. There are threats, and I hinted at it in the beginning when I talked about RSA cryptography and how it relies on this assumption that no one will be able to take a big number and find its prime factors, and so we can assume that all our secrets are safe. But we know actually the algorithm for solving that is already known with quantum computers. There's a very smart person called Peter Shor many decades ago. He already came up with that algorithm, but the computers are not there. But we are trying to make those computers. And so today, a lot of cryptography relies on these hard math problems. They assume that this hard mathematical problem cannot be solved. And if they are used in public key encryption, when anything is sent on the internet, there's a public key based transmission that happens. Digital signatures, these are used a lot in governance now and many things, right? Using digital signature, you can certify things. And they use these algorithms like RSA, DSA, ECC, all these are there, okay? And this is showing you, like if you have a long number like this and you want to find its factors, very hard. It'll take millions of years, even if you take the most powerful machine. But with quantum and Shor's algorithm, this is going to be in the hours range. So then what happens to all of our data? What happens to all of our communication, all of our security? It's pretty scary. Today, what is it? Today, of course, we don't have that. The threat today is this thing called harvest now, decrypt later. Which means Bad actors today, they can snoop and capture, say, network packets that are being sent on some network in India. Bad actors can probably snoop and keep capturing that. Now, they cannot see what is in it because it's encrypted, but they can store it. And then maybe after X years, when they can decrypt it, then they can decrypt and see what was there. And a lot of data of today will be relevant in a few years. After this notion of Q day being the day when somebody is able to break all these things, of course a lot of other things happen. You can of course decrypt this harvested data by stealing the keys. You can disrupt business by forgery. You can manipulate digitally signed contracts. You can do many things. This is probably not exhaustive. Now, what kinds of things it impacts? Internet protocols, everything we do on the internet, somewhere it's using one of these techniques. Digital signatures, a lot of critical infrastructure. When you're sending code updates to cars, for instance, or to anything, it's control systems. These all rely on some kind of security feature naturally. But all these security features use these same kind of codes. Financial systems, settlement systems like our SWIFT system globally, the India's RTGS system, blockchain, enterprise applications within enterprises, certificate authorities, all of these things. These are all potentially at risk. From a harvest now and decrypt later, this is just calling out kind of the life cycle of the data relevance. Like passports, right? Passports are relevant for 10 years. So if I can, somebody is sending passport related data on an encrypted channel today, but a bad actor harvests that and keeps it, cannot look inside, but say 7 years from now they can look inside, that data is still relevant because the passport is still active at that time, right? Road vehicles, critical infrastructure has an even longer life cycle, aircraft and trains. Then there are regulatory requirements there, like HIPAA requires you to store data, so that data stays sensitive and relevant for many years. Tax records have to be stored and are relevant and are used, you go back to tax records 5-6 years ago for different kinds of business reasons. So this harvest now, decrypt later is really relevant. It's not just about the data in that moment, because this data has a life cycle that goes into years and years.
Are you saying to prepare to protect today the way we keep our data? So how much time do you need? So this is all RTGS or basic systems.
No, that's what I'm going to get.
Sir. 2029, first fault tolerant specifications shows that the current.
Little bit after that. I will talk about it actually. Yeah, I will talk. मैं सब बताऊंगा. मैं cover करूँगा. So little bit about how, actually that's the question you're asking. When is this Q day, right? So there are predictions by expert institutes, right? So NIST, I'm sure आपको NIST पता होगा. NIST is they are expecting about 2030. There's University of Waterloo says 1 in 2 chance by 2031, 1 in 7 by 2026. Okay, I don't know if that is happening. It's kind of hard for me to imagine. But roughly you can see, right? Early 2030 is what people are thinking. But let's ground it a little bit. That is what people are saying. Like from an IBM lens, I talked about this, sir also said, right? 2029, this machine. And 2033, this machine that we are expecting to have, which is 2000 logical qubits. And something, this is just, our data center vision. In Poughkeepsie, we have a data center where these are the current machines, IBM Quantum System 2. This is what we expect this machine to look like, and this is what we expect the bigger machine to look like once it's built out. But that's the hardware story. There is an algorithm story also. because Shor came up with his algorithm in 90s or something like that. Since then, people are trying to make that even better and faster as a theory. And this sort of shows over the years how big of a quantum circuit or quantum program, how many quantum operations you can imagine need to be run to break, to factor the numbers. Okay. So we were somewhere here like 10 to the 11, kitna hua ye? Like 100 billion operations. And researchers have been bringing that down and down. Abhi March May, there was a very notable research paper that came out. I think it was Google and some others, where they showed that this particular cryptography, this is not all the cryptography I said, the ECDLP, which is also used quite widely, with about 1200 to 1400 logical qubits, in about 9 minutes, you will be able to break, right? Well, yes, but WhatsApp, I believe, is trying to move to quantum safe crypto, right? So at least private companies, I think, will be proactive because their business depends on it. If they don't, then yes. But yeah, but the key point is with this many logical qubits, 1400. And that is where this picture comes into play, because somewhere between these two is where 1400 is, right? This is IBM's story. I don't know what China is doing, right? Maybe China's time scales are different, right? But I think we don't know.
They must have
We don't know.
That's what it doesn't get out of that country.
We don't know, right? But they invest a lot more. Yes.
4-5 times than what you were saying.
Yes. At least at a public level. Yes. Not overall, but public investment. So that hopefully gives you a sense of when this Q day is coming. It's probably in the early 2030s sometime. And this is just sort of, I don't know why this is coming. Tell me. Oh, this thing is up. Thank you. Yeah, I think I made these points, so I'll skip this one. So what are people doing in terms of regulation? Maybe useful to know. EU is taking steps. They are mapping out a timeline where they're saying, 2026, by this year, they want to do a threat analysis and identify which systems are more vulnerable, risk analysis, things like that. By 2030, they want to mitigate the high risk use cases, and 2035 also transition all the medium risk ones to post quantum crypto. PQC is post quantum cryptography, matlab cryptography that is not breakable by quantum. UK also has a similar timeline. US for national security systems, not for the whole economy, but for national security systems, has a similar timeline. 2030 is one milestone for certain areas like software, firmware, traditional networking equipment. 2033 is for other things like web browsers, operating systems, things like that, right? India has not put out a roadmap yet. They have put out position papers, I think. DST has put one out. I see. It's very aggressive because it's not so easy. Yeah. Yeah. So I don't know if the execution plan is there, but they are okay. So where are we in terms of the PQC actually? Like, so what is the backup plan? So the good news is that a lot of work has happened over a decade or more on trying to find the alternative cryptography. A lot of experts are working on it. I don't think this. किधर लगाऊं मैं? Hand mic ले लेगा. I think hand mic better. Hello. Okay. So ever since 2016, NIST started this competition to say, okay, researchers come up with new codes, new cryptography that would be quantum resilient. And since then, a lot of progress has happened. Our IBM researchers have been very much involved in submitting proposals. And there were 4 algorithms that were announced a couple of 2-3 years ago by NIST as having selected out of that competition. 3 of those were either developed or co-developed by IBM. Some of these are already implemented into some of the hardware. For example, our mainframe hardware, which is used by a lot of banks. 70-80% of the credit card transactions globally are finally processed on IBM mainframe. So that's a very sensitive bottleneck. So we have already put in hardware that implements, the hardware has the implementation of these cryptos. So that allows then those banks to change their code software to use that. So there is progress happening at the hardware layer, software level, layer, theory layer to create the technology to allow people to migrate, at least to have the target to migrate to, which is the good news. And this continues, right? This initial set was addressing some of the cryptography use cases, but not all. For example, digital signatures was not addressed by it. So this work continues, and more innovation is needed. Like new standards were also published a little earlier. And what NIST is saying is basically some of these crypto like RSA, DH, ECDH, they believe they should just be disallowed after 2035 and deprecated 2030 and replaced by this MLChem algorithm. Similarly, these ones should be replaced by this. Whereas in Australia, the government is saying, no, we have to be even more aggressive. We have to disallow in 2030 itself, right? So people are looking at what is there and trying to create plans of migration. Many different countries have started looking at these things and creating guidances that they've published, and they are on the journey. This is actually coming from I think there's a website. I don't have the URL, but this QR code, if you scan on this website, it's a tracker for all the different countries, what kind of steps they are taking, where are they in their journey in terms of setting the standards for their own journey. Now, looking a little bit of how this plays out when we think about impact and migration, right? If you take an enterprise or an organization, what happens is you have business assets, that is where your business processes, your data assets, your applications are there. And you need to determine the criticality and risk. Then there's a lot of dependencies, right? It's not just that, oh, I'll fix here and everything will work. Like there's a lot of dependencies between applications and components. And then where are your cryptography artifacts? Where are you storing the keys? You have to go find them also, because many times all these have been built in an ad hoc manner. Some vendor is storing the keys somewhere. Like people don't even have an inventory of where these artifacts are. So the threat is to the cryptography artifacts, and the impact happens at the business level. And the people managing these are different, because the people owning the business application have no idea where the cryptography artifacts are. And the complexity comes because of all these dependencies, like who gets impacted because of a threat is happening because of these flows. Now, the standards are important to establish a standard way of doing this. We believe that this needs to move faster, both at an international level and at a national level. And then the guidance and legislation also needs to be much more, not just outlook, but execution plan, right? That can be moved into motion. So there are a lot of recommendations here that we present whenever we present about this to different stakeholders. What all are needed at this different levels. Skip through this. Now, when we talk about adoption, there are many personas that need to be involved in this process. You have your enterprise and strategy. Enterprise is just any kind of large organization that actually runs the business. where you have people like the CIO or the CTO or the Chief Information Security Officer. Then you have the compliance, risk, and cybersecurity teams. They have to be very much owning the strategy for how is this going to happen in the organization or in the department. They need to also understand where is the inventory, like they need to have the visibility and the plan. It is a gap. Yeah. You don't have an owner, right? Yeah. I mean, tools can be there. First is if you have an owner who knows that this is my job, then they figure out, okay, where to find the tools. Yeah. uh, then there are the actual business assets, the actual departments or businesses, the developers, all those methodologies of how we develop, how we deploy, how the business uses these things. That's not known or owned by this team, right? But they are very important in this process because the crypto is somewhere there, and the the change management happens over there. But then an important part is your third party, your supplier ecosystem, because not everything is in-house. There's some vendors who have implemented something, some libraries you've used, some software somebody has bought. If they are not fixing it, then that's your weak spot. So all of these have to have a plan that is coordinated and agree to it. This is a complicated one. I won't go through this. But generally, what it's saying is there is a way to think about this in some structured way, that across these three layers, how to go about understanding the risk, first of all, creating the joint awareness. This discussion we are having is somewhere here today. How to define the target state, like, okay, so where do we need to be? That needs to be defined clearly and kind of at a high level, the roadmap, and then execute, and how these different parties can be involved in that process. Broadly, if you look at the technology that's needed, there are these four pillars. One is you need to discover and create an inventory. Where all is cryptography used? Is it used for encrypting data at rest? Is it used in some communications? Is it used as digital signatures? Like, where all is it used? I need a way to discover and inventorize that. And there are tools that many vendors have built that are available to do these kinds of things. Second, if you have an inventory, then you can do assessment. You can assess what is my quantum cryptography risk. Like, okay, if I have it is in these 1,000 places, then these 1,000 places are there. And what is the impact of it, right? Which business applications are more critical? You can flag, which ones are the outdated one. Sorry? 100%, yes, but at least you'll know exactly where. Uh, then you need a way to manage the life cycle, because there's not a one-shot process that, okay, today it will happen. You need a program management to manage the life cycle of those things in a centralized way. Because if you leave it to every department, every team to just do it on their own with no single dashboarding and a life cycle management, okay, from now on, all the crypto inventory has to stay also visible. Not that I just discovered it once and 2 years later again I've lost it. So you have to establish a life cycle management mechanism also going forward that allows for all the interventions you need: automated key generation, enforcement of the consistent policies across, because we don't want to be in the same state 5 years from now. Maybe something else comes across along. Now we have to again change some cryptography. So it's also an opportunity to update our methodology of how we maintain cybersecurity. And then protect and adapt, which is the actual migration and actual implementation. One example, early days, is what Vodafone is doing. Telecom sector, of course, cares a lot about this. Vodafone has this product called SecureNet that provides digital security for their mobile customers. Of course, it uses a lot of cryptography, and they're working with IBM to update that and roll it out to their clients. So in the private sector, some activity has started. So in terms of how to approach this at a high level, what could be a roadmap? First step is educate. So everyone needs to understand what is this thing. That's what we are doing. Second is to start establishing some governance process about it, so that there is a structured way to approach all of this and to track. That will take care of this. Then you get into the things I talked about, right? In times to come.
Nine as the test year.
So sometimes you need to look at the hardware. Sometimes you can handle it at the software level. It depends on the application sensitivity. I gave the example of the hardware in the IBM mainframe because those are used for high-speed transactions. And so having the hardware provide very fast cryptography is very useful there. But if you are only doing, say, web authentication, not transactions, maybe the hardware doesn't matter. The software has to be updated and your data management has to be updated.
So, just one more question related to you mentioned earlier that more than half the credit card backend transactions and backend work is handled by IBM and its infrastructure. So, I mean, yesterday itself we had a session here with NPCI. They handle the bulk of digital payments in the country, in India, and even in so many other countries now. It's expanding. So, is there a threat perception in that ecosystem as well from this phenomenon?
I'm sure there is. I haven't.
Yeah.
Mostly, but
Yeah.
now, as we are that is being done, sir. Sir, actually, the entire roadmap of quantum migration, if you see, so it has 4 stages. So 2029, when we are talking about quantum migration, that will be critical infrastructure will be made safe. So that is 29. Then comes the third one, that is still 33. And after the fourth is 35. Identification is already started, sir. Because finally what he's saying, the Q day, nobody knows when it will come. So we're just saying 2030 to 35 anytime. So these timelines are probably. So those are critical. Those are critical DPIs. They will be taken care of. So that is already going on, sir. We are not aware.
In Operation Absolute Resolve by US when they captured this Venezuela president Nicolas Maduro and other. एक अच्छी बात सिर्फ ये होगी कि इसके बाद ईरान यूएस के वार जैसे वार ही नहीं होंगे. They don't need nuclear treaty. They need data
They
treaty.
need data. Next wars will be fought on data.
न्यूक्लियर का कोई समझ नहीं. वेनेजुएला प्रेसिडेंट को लेने के पहले उन्होंने सारे
Even at
डार्क कर दिया, पूरा डिफ्यूज कर दिया सिस्टम. डिफ्यूज भी नहीं किया, फेक सिग्नल देते रहे. एंड और पूरा लाइट जो पावर अप हो गया सारी जगह से. एंड 2 घंटे में सब करके गए. दे डोंट नीड न्यूक्लियर वॉर एंड अदर थिंग्स. वो 29 बहुत
Takes a lot of time to get.
yeah.
That awareness should be there.
नहीं एजुकेशन में रह जाएंगे तब तक डेटा उड़ जाएगा। मेरा ये कहना है कि गोइंग बाय स्टेजेस के बजाय वोडाफोन ने जो काम किया है मोबाइल डेटा इंक्रिप्शन और बाकी
Sir, luckily, India has one of the most well-defined programs globally for quantum.
That's why we were green in that map.
Yeah, we were green in that map. I
चाइना ने
noticed.
डिस्क्लोज नहीं
That's
किया ना
comforting.
the way with nvidia brought the gpu structure upgraded with the speed with
People like us may have a role to play then to make it better.
Yeah, at all levels, I think people can be proactive. Right? I think I mean, this is my personal opinion. Some of these things, while governance and all that happens, some of the pre-discovery and all can be done at the department level proactively, to get ready. Because once you are educated, you can say, okay, how can I be ready? Once the guidelines come and all, at least I know what will be needed. So things can be done at all levels. So once you discover, strategize, I think you already mentioned that, then do the transition. And then monitoring is very important. It's not a one-time thing. You need to then get into a new way. We actually call it crypto agility. See, until today, it was like crypto, done, forget. But now you have to be in a phase like, I know what my crypto is. Anytime I need to change anything, I can do it. I don't need to go through this cycle. So establishing that crypto agility or at an organization level will be an important new paradigm that everybody has to take. In commercial sectors, it's an opportunity.
that was the usp अब ये this was a new commercial sector more encrypted data
Will go out of vogue in 2-3 years.
Correct.
ये होगा ही नहीं.
हो गई
This piece of equipment will become obsolete.
बायोचिप्स आएगी
Some other way of.
yes neural implant
Yeah. So this is another way of kind of looking at this program. How one can think about program. Create executive understanding. This is more at a national level, but relevant to the state also. Create that sense of urgency across political and institutional settings. Create a quantum safe governance, so that there is ownership. The governance also means that who owns what has to be identified. Authority has to be given to the people who have that ownership. Coordination mechanisms have to be identified. Right? So while a lot of countries are saying by this will happen, but to go a little further when we talk about governance is those roles, responsibilities, coordination mechanism, empowerment, all that has to be put in place. What standards are going to be used for that execution? Right? That choice of the standards framework and whether that is the right one for your organization, for your state, those things is also part of this. And then comes the understanding your posture based on all of this, based on the inventory, doing the risk classification. This we already talked about. Creating the roadmap for transitioning, creating the implementation program. Another important factor is research and innovation, because this is not a vanilla migration project. This is a field that will keep evolving. And I'll give you an example. Those crypto safe keys I talked about, right? In theory, yes, they cannot be broken by quantum, but some of them have a challenge that the key is so big that if you have to now put it into your communication messages, your communications become slow. So it's not so simple. Now, if we decide we'll wait until someone else figures out all that, we will be the last adopters of anything. So organizations need some of their own innovators and thinkers to stay up ahead of the game, because this is not a place where we can wait for technology maturation somewhere else, then we pick it up, because the threat is very it has to be done in a collaborative way, because it has to be standardized. So it's not that everybody now makes their own thing, but everybody has to be in the same space, mental space of what is the state of the art and how do we all make it happen. capacity building, collaboration, I talked about that, and then monitoring and improvement. So it's kind of similar, but couple of new things here is this governance needs structure in it, right? Ownership, coordination, empowerment, all of these things, and research and innovation. These are two important things that sometimes get missed. I think that is my last slide. Thank you for your attention. Okay.
No, is there any interface between AI going rogue and quantum threat?
So, I mean, yeah, if you have vulnerabilities, then it's more vulnerable to rogue AI. That is a given thing. And one thing that's that AI is also starting to be get used for is to discover new quantum algorithms. Yes.
नमस्कार महाराष्ट्र शासन आयोजित टेकवारी
Can happen.
4.0 या ज्ञान तंत्रज्ञान आणि भविष्याभिमुख प्रशासनाच्या उपक्रमामध्ये आज दिनांक 6 मे 2026 रोजी दुपारी 2 वाजता परिषद सभागृह 6वा मजला विस्तार इमारत येथे फूड फॉर थॉट या विषयावर IHMT इन्स्टिट्यूट ऑफ हॉटेल मॅनेजमेंट यांचे सत्र होणार आहे. मंत्रालयातील सर्व अधिकारी व कर्मचाऱ्यांनी सदर सत्रासाठी उपस्थित राहून या उपक्रमात सहभागी व्हावे ही विनंती.
Thank you so much, Dr. Singhee, for bringing one of the most complex technologies of our time into clear and sharp focus. I now request Sri Subhash Umranikar Sir, Joint Secretary GAD, to deliver the vote of thanks.
Distinguished audience, our esteemed speaker, and dear colleagues. It's my privilege to propose vote of thanks for today's session on quantum computing, its uses, threats, and development. First and foremost, a big thank you to Sri Amith Singhee ji for having spared his time and come over here to deliver a lecture on quantum computing. Quantum computing is a field where, as the saying goes, if you think you understand it, but you don't understand. So thank you for guiding us through the complexities of this quantum computing. Thank you very much, sir. Again, I thank all those officers who have come from different offices. I really thank you and appreciate that your desire and efforts to understand the quantum computing subject. And all those who are watching this session live on the YouTube, I also thank all of them. I thank my core team, which has been playing a pivotal role in bringing all the departments together and organizing a session like this. Thank you once again. Thank you, everyone.
My pleasure.
Another very good one.
Thank you.
I think we are in some. Yes, someone here.
Almost there.